In the last lecture, we were looking at the Cartan subalgebra for 03 and the Casimir operators. And we said, rather than use the L operator, Lx, Ly, and Lz, let us call it J, and take the commutation rules Jx, Jy to be IH bar Jz, with cyclic permutations as before. It's then we could verify that J squared, Jx squared plus Jy squared plus Jz squared, does commute with all of the J's and therefore is a Casimir operator, as we discussed last time. We can take the Cartan subalgebra to be any one of the J's, but only one of those. And we take it to be Jz. We then defined a J plus and a J minus to be Jx plus or minus I Jy. And then we can show, and we begin this lecture with the fact that one can then show that Jz times J plus is Jz times Jx plus I, of course, times Jz Jy. And all we have done is substitute this expression in here. And Zjx is IH bar Jy. Jz Jy is minus IH bar Jx. So by pulling the H bar outside, here we have two I's, a minus I and an I, and that gives us a plus Jx and an I times Jy, which is in fact J plus. It follows therefore that Jz with J plus is H bar times J plus. Likewise, it's trivial to then show that Jz times J minus is H bar times J minus with a minus sign out front. The commutator between the two of these, J plus and J minus, is then easy to show is 2H bar times Jz. And we recognize this as the Cartan normal form, with our Jz is equal to our H operator that we've discussed before. Our J plus and J minus is our E plus and E minus, and our J squared equal to C, the Casimir operator, where we will set H bar equal to 1 for the following work. Now, it's important to remember that when we have the H operator with the E plus or minus operator, we'll notice that we get exactly what we get here. Plus, and also we get E plus and E minus is always going to give us the H operator or some linear combination of those. And here we get 2H bar times that. Setting H equal to 1, we will continue with looking at this algebra and its eigenvalue spectra. We continue now looking at the orthogonal group in three-dimension Lie algebra. We're going to look at the eigenvalue spectra. Let's remind ourselves generally that for a Lie algebra, a maximum commuting set of operators are the whole set of Casimir operators plus a whole set of D operators, which are Casimir operators for the subalgebra that all commute with the H's, and the H's is a maximum commuting set of operators within the algebra itself. Consequently, since all of these operators commute, we can look at their eigenvalues in lowercase letters as a small c1, c2, and so forth, d1 and d2, h1 and h2. And that labels all of the eigenvalues for a complete set of commuting operators with the c's, the d's, and the h's. In the current case that we're looking at, we only have one c, which is j squared. There are no d's, and jz is equal to our h. We therefore label the eigenvalues by two variables, m and j, as follows. We let the eigenvalue of the j squared operator be represented by a j when the eigenvalue is j times j plus 1 back times the state again. Likewise, we will represent the eigenvalue of jz as m, where jz times jm is m times jm again. So these are eigenvalues with the small j and the small m as being numbers. And what we want to do is determine what the properties of those numbers are. What are their characteristics? We will need certain identities in order to show that. First, it can be easily shown that j squared is 1/2 of j plus j minus j plus jz squared. From that, one can conclude that j minus j plus is j squared minus jz times jz plus 1, and j plus j minus is j squared minus jz minus 1. Now we'll be using these three equations in order to derive what we need to derive. Namely, first, we show that if we act with a j minus and a j plus times jm, then of course we can use this form right here. And both the j squared and the jz have are eigenvalues, j and m, and therefore we can immediately get, when the j squared hits a jm, we get j times j plus m, minus this term, which will give us the eigenvalues m times m plus 1, all multiplied by the vector jm. Now, we can rewrite that expression as j minus m times j plus m plus 1. Likewise, we can take j plus j minus as this term, multiply it by the vector jm, and since j and m are the eigenvalues of these two operators, we immediately have again j times j plus 1 minus m times m minus 1 here. And that can be rewritten in the form, and these are just numbers here, j plus m times j minus m plus 1. And of course the difference between these two is the sign right here and the sign right here. It only takes a second to multiply this out and verify that they're the same things. It follows that the norms of these vectors, j plus and j minus, are as follows. By taking the j minus j plus and sandwiching it between two jm vectors, we can look at the norm of this vector j plus times jm times its dagger, which would be the j minus acting backwards on the jm here. Then, since that gives us j minus m times this other expression here, times jm times jm, it follows that we've related the norm of this vector to the norm of this vector and some coefficient. Likewise, we can take the norm of j minus times jm, and when it is multiplied by its Hermitian conjugate, we get this, which gives us this, times jm times jm. The techniques that we are using in the process of looking at the rotation group are exactly the same techniques that one uses looking at any of the Lie algebras that are semi-simple, whether that's SU2, SU3, SU4, or any of the other algebras. Therefore, we're not so much talking about this exact algebra as we are looking at a very elementary case of a Lie algebra and how you find the eigenvalue spectra. So we will continue now looking for the eigenvalue spectra of O3's Lie algebra. I'm going to keep part of that page in front of us that we just completed so that we can see the norms of these vectors here. And as we go forward in looking at the eigenvalue spectra, the first thing that we want to do, and recall that we are using h bar is equal to 1, the norms of vectors cannot be negative. It follows from this, in these equations right here, that j minus m times j plus m plus 1 has to be greater than or equal to 0. Since this is the norm of the vector j plus jm multiplied by its own dagger, and this is the norm of the j minus jm vector, and here's a norm here, and here's a norm here. This is greater than 0, this is greater than 0 for both cases. Therefore, it follows that this must be greater than or equal to 0. Consequently, also, this other term, j plus m, j minus m plus 1, also has to be greater than or equal to 0. It follows then that since both this must be greater than or equal to 0, and this must be greater than to equal to 0, it follows that m must be between minus j and plus j. That is because if m were to be greater than j, this would be negative and this would be positive, so the product would be negative, and that's not allowed. Likewise, by that same token, m must be greater than minus j, otherwise if it weren't, if m were, say, minus j plus 1, then although this would be okay, this would not be okay, this would be positive and this would be negative, which is also unallowed. It follows that, therefore, that m must be less than or equal to minus j than j and greater than or equal to minus j. So it's sandwiched between the negative and the positive values of j. Thinking back to the norms that we previously had in our work here, then we realized that the norm of this vector here is positive, the norm of this vector is positive, and the norm of this vector can be 0 only if this quantity here vanishes. I've written it out explicitly right here, and we can see that j plus times the vector jm can be 0. In other words, the norm of a vector can be 0 only if the vector itself is 0. And that can happen if and only if the quantity that multiplied the right-hand side was equal to 0 exactly. And that can equal to 0 only if m is equal to j. Likewise, j minus times jm can be 0 if and only if, and that's because this norm can be 0 only if the vector is 0, and the vector and the norm are 0 on the left, requires that on the right-hand side the coefficient vanish, because the vector could not. And that can be the case only when this is equal to 0, and that can happen only if m is equal to minus j. Now we recall that jz times j plus is j plus again, just like Cartan's relationship that h with the e plus alpha is a vector r sub I of alpha times e alpha again. And we're going to rewrite this as jz j plus is equal to j plus jz plus j plus. And we're going to act on a jm vector. And when we do that, we're going to take, in other words, we're going to be looking at this j plus jm to see what kind, and this is the thing we're looking for now, what eigenvalue of jz does this have? We know that this vector right here has an eigenvector, an eigenvalue of m for jz. But what happens if we act with j plus first? Well, we take jz times j plus from this equation right here and multiply it by this equation. And that's important because now we've taken the j plus using that commutator and put it in front so the jz can act directly on the jm. It will of course pull out an m and leave us with j plus jm. Likewise, we're left with a j plus times jm here. Altogether then, the first term will give us an m, the second term will give us a 1, and multiplied by j plus times jm. Consequently, it follows that j plus times the vector jm is some kind of coefficient with normalization and so forth times a vector that has the eigenvalue j and the eigenvalue m plus 1. We have just shown that the eigenvalue of this vector here of Jz is m plus 1. Therefore, we can say J plus times Jm is something, some number here, coefficient, times J of m plus 1. Now, none of these vectors actually can change the value of J. That's because J commutes with everything in the algebra. So consequently, nothing raises and lowers the Casimir operator. And that is later on what we'll see that defines what is called an irreducible representation, one that is separated out for a particular set of the Casimir operators. But the J plus and the J minus, or equivalently the E plus and E minuses, do move us around in the entire Cartan subalgebra, in this case just the single values of m. So in general, you'll recall that the E plus or minus, E plus alpha operator will always change HI to an HI plus RI of alpha. We find that the J minus also lowers this, and we get a J minus times Jm is equal to some coefficient times J and with an m minus 1. So summing up now, we realize that the J plus raises us by a value of m by 1. The J minus lowers us with a value of m minus 1. But yet m is bounded on the bottom by minus j, and it's bounded at the top with plus j. So we can take a given vector jm and act p times with a j plus to raise it and raise it and raise it until finally we get a jj. Namely, we've raised the eigenvalue m as far as we can, and if we try to raise it any higher, we'll get a null vector. We could likewise lower it q times with j minus to get j and minus j, and we cannot lower it any more without getting a null vector. But both p and q are integers, and they're both non-negative because we've done this a positive number of times. So p plus q, as the sum of two integers, must give us twice j, and therefore we get the spectra that j must equal to, since the sum of two integers is an integer, a half of an integer. Or j is equal to 0, 1 half, 1, 3 halves, 2, which is of course 2 over 2, 3 over 2, 4 over 2, 5 over 2, and all of the spectrum of the half integers beginning with 0 and going all the way to infinity. For each one of those values of j, then we have the value of m going from minus j plus 1, 1 greater, minus j plus 2, until we get to j minus 1, and then finally to j itself. We have now derived the entire eigenvalue spectrum for both m and j for O3. We continue with the orthogonal group in 3 dimensions. We have just shown that the norm of j plus times jm is j plus jm times its Hermitian conjugate vector, which is this vector right here. Now, if this vector that we started with had a unit norm, then it would follow that we had increased the norm by this value for the entire scalar product. So, if j plus always acted along with the square root of this value, it was divided by the square root of this value, then when we acted with this and took its norm, we would get 2 of these square root factors, which means that the norm of this object here would be the same as the norm of this object here, and therefore we would have a system with the raising and lowering operators, and the lowering operator by this, which would never alter the norm as we moved around. Therefore, we define any of the states from another state that has a unit norm by using a j plus and a j minus that have exactly these values here. That way we maintain the norm. It's also important to realize that we've done something else. each one of these vectors is orthogonal to the others. And that is because these are eigenvalues or eigenvectors of Hermitian operators with different eigenvalues. Now, if we want to, we can choose the phase of these, e to the I theta, times any one of these vectors to be anything we choose. And we would not be able to observe a phase relationship between any of these two vectors that are orthogonal to one another, because that would be unmeasurable. So we have this arbitrariness of phase, and we would like to define a phase relationship between these vectors using the raising and lowering operators, and we do that with exactly these equations here. In other words, we define the phase as no different from the phase of the vector which we are either raising or lowering. In other words, we do not put an e to the I phi out here, where phi is some phase that's dependent upon the number of times that we have raised or lowered the operators. So consequently, by acting with this e plus operator here and this e minus operator here, we can raise and lower the eigenvalues and maintain the norm, so that if we start out with a vector that has a unit norm, we maintain that vector, and furthermore, that defines the relative phase as being real and unity. Well, the approach that we have been using is essentially the same for all three Lie algebras. The XPI algebra, which is the Heisenberg algebra, the XPIN algebra, which was the harmonic oscillator, and the JX, JY, and JZ algebra, or the O3 algebra for the rotation group. Namely, what have we done? We have put the Lie algebra in Cartan normal form. We use the e plus and e minus operators and the norms of the vectors to determine the spectra of the eigenvalues. And thirdly, we have re-expressed that in terms of position space to get functions that solve the differential equations. Well, we did that for x and p. We did that for the harmonic oscillator. But we have not yet re-expressed these vectors here, the J, M vectors, in terms of a position space. That can only be done not from the abstract algebra J, X, J, Y, and JZ, but only from an algebra L which is well defined with respect to X and P, namely the orbital angular momentum. So we can now seek to define the orbital angular momenta back in terms of the position space, and that will lead us to the study of special functions called the spherical harmonics.